We're going to be doing some assembly language programming today. We did a lot of assembly some previous streams. This time we'll be going through a refresher of the things that we went through so far, and then proceed onward to chapter 3 out of a whole bunch of different chapters. There's a lot of different chapters, and there's a lot to learn with assembly, and I'm having a lot of fun with it. It's becoming obvious what's going on, what's happening. We'll walk through some of the code again just to get things started. We will look at the beginning of the tutorial, and we'll read through it. We'll read through this together. So here we'll start here at the top of the screen. If you're going to walk through this tutorial with me, or if you're at a computer, you're going to be needing to use a terminal app. This will give you access to the command line and will allow you to execute the assembler and the linker. You'll also, if you want, you could use a terminal window to edit the assembly files directly, or you could edit the assembly files in your favorite text editor. You don't have to use the terminal. To get started, all right, so we have a terminal window. Crust is a real thing, by the way. Is it really unsafe Rust? That sounds dangerous. It sounds dangerous. To make the Hello World applications, this tutorial already made some changes, so it works on ARM processors better. The system call in Linux and Mac OS have several differences due to the unique conventions of each system. Here are some of the key differences. Function number. The function numbers differ between the two systems. Wait, really? Linux using 64 and Mac using 4. Really? To make the linker work, a little more is needed. Actually, it's not that hard. I remember doing this. So let's try this really quick. Let's see if we can get back up to speed with the first Hello World. So let's copy this. Copy. Okay. And then we're in the first, let's see, CD chapter 1. Okay. So hello world.o for the object file. And this will be, okay. So this will assemble and this will link, right? So these are two separate things. So we've got two phases here in the make file. With the output will be O, and then we link it. Okay, so LD, L system. So which do we do? What happens first, right? So it seems like this happens first, right? Because we need to make the O file, and then we assemble it over here. Assembly first. That's what I thought. Because the linker has to come last, right? So assembly first, and then linker second. That makes sense. That absolutely makes sense. Happens first. Yep. AS first for assembly, LD second for link. So we should just be able to run make, and that should work. So ls rm hello world and .o and hello world. So that will remove all the build files. And so if we run, so let's see, if I make file real quick. If we just run the assemble, so assembly first, right? We assemble. That will make the object file. Let's see here, which is right here. That's the assembly, right? So let's see again. So now we can do this right here. So let me see here. Let me bring this over here. Let us do this and then / this. Okay. So we should be able to copy and paste this right here. And let's see here. Let's do this. Copy, paste here. All right. And then we should be able to run that. Okay, there we go. And that creates the binary. Let's walk through the very basics of this Hello World program here. This is going to be printing out. I do believe this is going to be printing out. We're going to do a supervisor call. We're going to be moving data into registers. And we're going to have an entry point of start, which tells the system where to start running the code. Right? There's a start. And so here's the start, right? The start's right here. You can see it starts. This is the start, the global start. This is the start of the program. The first thing we're going to do, and this indentation is just for pretty. You don't need to do that. You don't need to do that. So let's close this really quick. You don't need to do that. We should be able to chapter 01. Let's go with this. You're right, the tech man. Of course, I should have said code. You're right. I should have. Okay. So let's see here. Start. And then the start is here at the top. Here we go. I tell you what, here we go. Let's do this. Let's close this. Actually close it. Thank you. Okay. Move. So now what we're going to do, move, we're literally going to take a literal number 1, and move it into register 1. So we're going to move it into register 1. I'm going to make this, I do believe we should be able to, build, I believe this should build. So we should be able to just run make. Let's just run make. Okay, so that still builds. So we changed up some of the syntax. All right, so move to register 1, which we're going to set the value 1. This is the register 1. We're giving it the literal number 1. Just the literal number 1. And this is the input parameters to the function that we're going to be calling. And then parameter 2 is the pointer to the string that we're going to be printing. And that is defined here at the bottom, line 27. So register 2, or well, the second register, which is register 1, right? Register 0, first register, register 0. It's confusing. I know it's confusing. Don't worry about it. X1, which is the second register, will be the starting point, the address of hello world, which is the string. And then X2 will be the length of string. So you can say less. You can reduce this, right? You can drop that down and it will print fewer characters, right? It'll print fewer characters. So how many characters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. Because this is a new line character. It's a new line character. The old code? Wait, Neva, what old code are you talking about? Maybe? I don't know. Okay. Let's get back into this. Why did that not work? That should be printing out exactly 10 characters. Let's rebuild that ls. Here we go. Let's rebuild that. rm hello world and hello world dot o. Okay, make dot / hello world. Okay, so now it printed out hello. It printed out hello world without a d. Was that because I put the \0 there? What if we put the \0 here? Let's see. Let's do like one. Let's do extra characters here. Let's do this. Let's go here. Okay. Let's rebuild, make, and then rerun it. Okay. So it is working. Okay. So it's doing what I thought. It's just that I might not have removed all the things that we needed to remove. Okay. So we're on the right track. We know what we're doing here. We know what we're doing. Yeah, so you're running the older code. Yep, that's what it was. I was absolutely running the old code. I believe we should be able to. So let's do this. rm hello, and then hello.o, and then make, and then dot / hello. Hello. All right, we did it. As you can see here on screen, just the word hello. Just the word hello. We got to print it. These are all the different system calls you can call. So right here, this is the line where you say what system call you want to call. You just put a literal into X16, the X16 register. It's different on different assembly targets. It could be R8, for example, or a different register. You just use Linux syscall table. It's 99% compatible. It is, yeah, that's what I want. You got it. You got it, Simone. You got it. This is exactly what I wanted. I like this. All right, so where is open? Open. Here we go. So we could do open. We could learn that. We could write. We could read. We could even read. Check that out. You could fork. You can exit. And I do believe this is the exit right here. All right. It's back there. Tab in. Okay. Pretty neat. Pretty neat. Link and unlink. Not sure what's that about. Oh, you can make directories. You can do different system call things here. You can accept inbound data. Get socket stuff. Networking level stuff. Syscall? You can do syscall? You really? That's crazy. I didn't know. Get a whole bunch of different things here. Anything you want on the system. Except reboot. You can reboot. To add example 1. That should be able to run. And then we've got a trace trap because I think I had a break statement here. So we should be able to comment that out. Clean. And then make again. And then rerun that example, and it should not trace trap. Okay, excellent. Let's add that back, re-clean everything, and then remake it, and then do LLDB add. Wait, can I paste that? No. Let's see here. Let's do this. Copy that. LLDB and then we allows you to. So if we're still following along here, I'm still trying to like make progress here. If you're still following along, we just ran the program with a break statement, which allows us to track the value of each of the registers. So like W0. At this point, W0 should be 4, right? How do we print out W0? Debugger. It's like a debugger that you can use to debug things. It's like a regular debugger, so any kind of debugger. But it's best for, in our case, for disassembling, right? So I do believe you can say disassemble. I know there's a disassemble command. So like, let's check this out. Vi readme dis. There is a disassemble. Here we go. So if we run this command here, I do believe we could disassemble the code. Here we go. There you go. Check it out. Isn't that neat right there? Look at that. Well, it's a lot more than I thought it was going to be. What's going on here? Wait, what's happening? Why is there so much? What? Hold on. Let's close that. Okay. Look at this. What is that can't be right. That's insane. There's not even that many instructions. What? It should. That's just ridiculous. LLDB is for linking, I believe. LLVM or LD for linking. LD for linking. LLDB is for debugging that. It's the same as GDB, but on Mac. You got to run it on Mac. LLDB for Mac. If you get the LLVM release, you get a debugger with it, assembler Clang, CLang linker. It's like a lot of tools. You get a lot of tools. Yeah, you do. You get a lot of tools. Yeah, it's really cool. Nice. System symbols and other executable wrapping. That's what it is. Oh, got it. That's why it's so much. You're seeing the linked in code like all the Dyn stuff is linking. Got it. Okay, so that's just a lot. There's just a lot. DY enter. Yep, a whole bunch of stuff here. That's why. Okay. That's why it's 17 kilobytes. And the actual assembly file that we have here, add one, is only like, it's not even a kilobyte. It's not even a kilobyte. That's crazy. Let's see. Can we say disassemble straight like this? No, we have to say start. And then it gives us a whole bunch of stuff. Note that because we are linking a dynamic executable, the listing will be long and include other start functions. Our code will be listed under the line move example start. Likewise, the LLDB wants the breakpoint name without the underscore be start. Okay. To get the registers, this is what we like. We like the registers, you guys. We like the registers. To get the registers on the LLDB, we use register read. Although print seemed to do just fine. Register read, so R. So memory read, read, R-E-R, SPX1X0. What is this? What does this do right here? I'm looking at this right here. To get the registers on LLDB, we use register read or reread. Without arguments, this command will print all registers, or you can specify them. All right, let's do it. Let's check it out. Oh, okay. All right, let's see. Make. Okay, so let's see. Make. We are good. Let's just remake everything. Make, clean, make, and then LLDB. Add example 1. Run. Enable permissions, and then there was a break statement. Is there a continue? Continue. I think we're fine. We'll leave it there for now. So let's follow this example here. RER. So our register read. Whoa! Look at that. Check it out. This reads all the registers. Why doesn't it? Oh, look! It says this is neat. Look at that. Right. What happens when we don't do a break statement? What happens when we don't break? Make and then run and then wait, LLDB exam. Oh, okay, yeah. Run, allow, okay, exited, okay, Are the registers still there? Reread. Reread. Okay. Register read. So you do need a break statement. Command requires a process which is currently stopped. Okay. W and X's are sizes. Oh, so it's still, X is extra large and has the full 64-bit. W is half size. Got it. All right, Neva, thank you. That's great to know. So technically, we should be able to do that. Are these different registers or are they the same register? So if I do X and mix in X and W, can you do that? Is it possible? Can you do that? Let's do make clean, make, and then LLDB add example 1. Go. Run. Okay, allow. All right. Now, read. Register read. You can. It does. You can mix register X's and W's. You can mix the register X and W's. W is for the smaller 32-bit, and X is for the very large. Hey, check this out. You can mix them. I don't know why. So then why would, well, if you're trying to, like, I guess, maintain a limit on your addresses, I guess, or your values in the register, you can basically zero set automatically the top stuff. All my experience seems impossible. Perfect distance from the sun. Perfect lifespan. Not interpreted all the data. Perfect tech phase transition.